time horizontally, the bullets would be on the ground at the same time. Okay? The difference is that this bullet is going to go really far that way before it actually gets to the ground. So, you know, the first bullet that I'm holding in my hand just drops straight down. The second bullet that I shoot horizontally like that, it's going to go like this. You can't tell. Can you tell that's dropping? Yeah, it's dropping. It's going to take the same amount of time for it to actually hit the ground, but this bullet's going to be way down there before it actually hits the ground. But it'll take the same amount of time, which is why, like, sharpshooters and snipers, they have to understand how far something is away, because if they're going to try and shoot something really far away, they need to know how much their bullet's going to drop before it actually gets to the target, because you can't stop gravity, right? So they have to take into account all sorts of things, right? Distance, humidity, temperature, wind, all these different things, and try and put things on target. So how is this related, and why am I telling you all this? Because imagine that I were to shoot a bullet so fast, okay? So that I'm shoot this bullet, it's traveling so fast that as it starts to drop, okay, it's dropping, right? As soon as it comes out of the barrel, it's dropping. Imagine it's going so fast that as it drops, the curvature of the earth is actually dropping away from it as well, right? Because when you're on Earth, I hope we all agree that Earth is not flat, okay? So what I'm saying is, what if I shot a bullet so fast that as it tries to drop and hit the Earth, it's traveling so fast that as it's dropping towards the Earth is actually curving away from the bullet as it tries to drop. Does that concept make sense to you? That's what satellites are. Okay? That's what a satellite is going around the Earth. All we do is we send something up into space, right? And we get it traveling so fast. There's a certain, you know, height and speed you need to be at. And once we get to this certain height and speed right there at that point, we cut the engines off. There's no more acceleration. We turn everything off and we just let it fall. And as it falls back to Earth, because it's traveling this direction fast, it starts to fall towards the Earth as the Earth curves away, and it just gets stuck in a perpetual falling motion around the Earth. And that's what orbit is. That's what satellites do. Does that make sense? It's pretty awesome if you think about that. The moon, right? The moon, right? It's going around the Earth. The moon is falling towards the Earth all the time. It's always falling. It's just traveling so that it never just keeps going around. It's kind of cool when you think about that. Okay, I'm just going way off on. In another life, I'm a physics teacher. I tell you somewhere. Okay, let's do this. I'm going to give you let me give you two problems just based on everything I just told you. All right. First problem is this. A rock is dropped from a 60-foot bridge. First thing, find quadratic function for this situation. Okay? Does that make sense what I'm asking you? This is exactly like the experiment we just did with 7 feet. In a pen, it's basically 60 feet with a rock, right? So you come up with the equation. The next thing I want you to do is I want you to find how long it takes for a rock to hit the ground. That's the first question. The second question. A rock is thrown upward with a speed of 160 feet per per second, that's really fast, from the same bridge. So in the first scenario, first question, I say, hey, just drop the rock from the 60-foot bridge, right? Drop it. Tell me how long it takes to hit the ground. Find the function, then tell me how long it takes to hit the ground. So we set it equal to 0, right? That's what we did. Here, instead of dropping it, I'm throwing it up, and I'm throwing it up really at a really high rate of speed, 160 feet per second. But it's the same bridge, so we're still 60 feet off the ground. My first question is, find the quadratic function for this. The second question is not how long it takes to hit the ground. The second question is, find its maximum height. When I say it, I'm talking about the rock. I want to know how high it goes. See, over here I drop the rock, right? From 60 feet, I drop it. The highest it ever was 60 feet. Here, I'm throwing the rock up. It's got to go up and come back down, right? Up, come back down, up, down. What's that point up there? Vertex. This has to do with the vertex, doesn't it? Something here has to do with the vertex. I want you to find its maximum height. And then for part C, I want you to figure out how long it takes to hit the ground. How long does it take to hit the ground? It won't be the same answer as the first question, right? It won't be the same answer because you've thrown the rock up. And as a final kind of reminder here, just in case you don't have it, d of t equals negative 16 t squared plus v naught t plus d naught. D naught is the starting height. Starting height, starting velocity, right? Positive if it's up, negative if it's down. So is our v naught going to be positive or negative on the second question? What is our v naught? I'm really giving you all some hints here. On this question, what's d naught in this question? What's the starting height? 60-foot bridge still, right? V naught here is not 0 here, right? It's 0 here. It's what? It's the 160. Is it positive or negative? We're throwing it up, it'll be positive. So V naught here, in this question, V naught will be positive 160. Understand? And then you have a quadratic. And then you can do all this because you can come up with a function, you can find its max, that has to do with the vertex, and then you can figure out how long it takes to hit the ground. That means you're going to need to set it equal to 0. You'll probably need quadratic formula for both of these. Let's see how that goes. Why don't you try those problems for next time, and we'll talk about them, right? Just have it done on a separate piece of paper. I want to see that you at least tried them. You might run into issues, all right? All right, that's it for today. We'll come back and do rational functions on Thursday. Y'all have a good one. Get in here real quick.